Our next speaker is Rasmus, Larsen, and he'll be telling us about how to perform segmented reductions on GPUs.
Yes, I will. So this is work together with folks from the University of Copenhagen. I'm going to start by telling you a bit about the problem that we're trying to solve. I'm not assuming that many people are familiar with segmented reductions. So start off by, hopefully, you guys know what reduction is. We take a reduction operator and list, and we produce a single value as we can see here. For our work, we require that the reduction operator is associative, meaning that the way you set the parentheses does not matter. And we require that the E here is the neutral element, such that applying it to the reduction operator is just identity. And for this talk, we'll call these non-segmented reductions, just to be clear on the terminology. So what is a segment reduction? Well, it's a reduction for inner arrays of a multi-dimensional array. And we'll call these arrays being reduced for segments. So, as an example, here's a two-dimensional array. If you want to compute the sum of each of the inner arrays, we're going to have two segments. And we can do this computation by mapping over a two-dimensional array and then performing a reduction inside. In this case, we get two results, one for each segment, and these are the numbers, who cares? In this work, we require that all multi-dimensional arrays must be regular. This means that all dimensions have a fixed size. So this example is not. This means that really we can kind of ignore the dimensionality and just focus on the number of segments and the segment size. We'll kind of write this in a C-style array fashion. Just so you know this notation. Kind of silly type. If you do a segment reduction over a number of segments of some size, you'll end up with one result per segment. So what's the problem, you might ask? Well, the problem is that the initial implementation used a segmented scanning. And it's not really a problem, it's an okay solution, but it's just not very good. Or it's not like super good. So what does this mean? It means if we have this input array, and if we do a segmented scan, we'll compute all the intermediate values, install those in memory as well. And then we can pick off the last elements as the result for our segmented reduction. So that's one way to do it. Intuitively, writing all these values for the segmented scan to memory is a bit expensive. So we can look at the performance of this. So we'll see this figure a couple of times, so I'll just try to explain it. We're looking at the runtime, and we're looking for it over different compositions of the same number of elements. So in this case, we're looking at 2 to the power of 26 integers that we're performing a segmented sum for. Here on the right, we're looking at one segment containing all the elements, then 4 segments containing a quarter of the elements, then 16, and so on. Until on the right left, we have one element in each segment. We can see it's fairly stable. Okay, you might think, yeah, well,
What's the platform here?
what's the platform here? It's an NVIDIA K40. And this is running from Stack. I'll get to that in a minute. So, you might think, hey, this is good enough. Who cares? So, to compare against something, we're looking at what's the performance to do a non-segmented reduction over the same amount of data. We got that down here in orange. So there's a big gap. And really what we want to do is we want to create a new function that is all the way down here. And that's kind of a bit too optimistic. In the far end over there, we're going to write way more results. So writing 67 million results to memory versus just one, it might take a bit more time, but that's kind of the optimistic goal. And that's what I'm going to discuss in the rest of this talk, how we try to do that. So just to give an idea about the framework we're working in, it's full time. So GPUs really offer an excellent opportunity to get high performance computing done. But writing OpenCL and CUDA is not really that fun, and it requires a lot of expertise knowledge. So FUTAC is a purely functional array programming language. It supports nested data parallelism, all array operators such as map, reduce, scan. The compiler can generate high-performance code for GPUs using OpenCL. And the idea is really to allow non-expert users, or at least non-GPU expert users, to write code more easily and still get good performance. They might get better performance by spending a week tuning CUDA code, but who has time for that? This webpage if you want to learn more. And a disclaimer, the core part of this work really has nothing to do with functional programming or the full-stack language. It could be applied to any GPU library that wants to do segmented reductions for regular arrays. There are some details in the paper where we actually use like fun stuff in the compiler, which is functional, so yeah, check that out if you want to learn more. So, because we're going to talk about GPUs, I'm going to give a quick primer on it, just so you're able to follow along. So the way a GPU works is that you launch a number of workgroups, each containing a number of threads that will all execute the same function, which we call a kernel, because why not? A web of threads will then execute the same instruction concurrently in a SYND fashion. GPU can have many threads running at once. For this particular GPU we're looking at 30,000. To get good performance, we really want to run many threads, all of them at once. And we want to have them do useful work all the time. The second part that you really need to get right is to access memory in the right way. It's called memory coalescing. And the simplified version is that thread I and I+1 in the same work should access array elements j and j+1. So we can have a small example here. If we have 12 elements and we're working with 4 threads, we're going to go through 3 iterations to read all the elements. The way we should do it is 1, 2, 3. This will allow a single memory transaction for each iteration. If we instead did it like this, 1, 2, 3, in the worst case, we would have to do 1 memory transaction per thread per iteration. So we're looking at 3 memory transactions versus 12. And this is super important for getting good performance. So how do we usually do reductions? Well, we split it up in this tree-like fashion, and we can give a part of it to different groups and then reduce it recursively. That's good and dandy. However, we also have special support for commutative evaluators, meaning you can kind of flip the arguments and still get the same result. And then we can do something like this. And you might wonder, why is this important? Well, when it's commutative, we can very easily do this memory coalescing if you want each thread to read more than 1 element before doing the reduction. And when it's not commutative, we can't really do that. So we, in a full-stack compiler, we do a trick where we do a transpose, and then we can kind of do it. I'm not going to go into the details. I'm just going to let you know that we want to do this, and we have to pay a price of this transpose to be able to do that. There's a special reduce com, to mark that it's commutative. So that's it. Now you're all GPU experts, and we are ready to look at the actual work that we did. So the overall idea is that there's no silver bullet. There's no one function that we can create that will work well for all these different combinations of number of segments and segment size. Instead, what we'll do is that we'll develop multiple strategies, and at runtime, we will, so they're all specialized to handle some cases well. And at runtime, we will choose which strategy to use depending on what kind of input data we're looking at. And to keep things simple, when you run the compiler or when you run the program, you specify a group size that you want to use and keep that constant overall. And you specify a minimum number of groups to use for the GPU. There could be some optimization by varying this, but to keep things simple, this is the way we do it. So to get started, the first strategy is simply just copying, hey, what did we do for a non-segmented reduction? Maybe we can just use the same thing for some of our cases, and we can. So when the segments are large, relative to the group size, then we can make use of multiple groups to process the same segment. So in the picture here, we see 2 segments. we have 6 groups, and we use 3 groups per segment. This will give us multiple results per segment, and these will have to be reduced recursively later on to get a single result per segment. We can also make each thread with multiple elements, as I discussed before. We call this chunking. And for the non-commutative operator, we also have to do this transpose thing to get memory coalescing. Important thing is here that we will process at most 1 segment in a group. So all we have to decide is how many groups do we want to run per segment. We simply say use at least this optimal number of groups that you specified when you ran the program, and we make each thread reach so many elements that all the elements are read by the threads that we're using. What's the performance like? Here in blue we have it, and yes! We actually got it down there, but that's kind of an obvious thing because we use the same strategy. So for these first cases, we have a few large segments, or at least they're large enough that we can get a good chunking factor, so that's good. And actually, this point in between these two, we have the case of the group size is equal to the segment size. And then when we go further to the right, the segments will be smaller than the groups. So only a fraction of the threads in a group will be active, so we get horrible performance. So to handle those cases, we do something else. We use a small segment strategy. So again, relative to the group size, when the segments are smaller, we can process multiple segments within one group. And to avoid communication costs between groups, we disallow to split a segment between multiple groups. So in this case, again, we have 3 segments, we have 2 groups, we can fit 2 whole segments in one group. And we could have taken part of the orange segment and put it with the others. But we don't want to do that because we want to avoid that cost. So, yeah, that's really it. Again, we can look at the runtime, at the performance for this. We can see that on the right here with the red squares. And we can see that we're actually covering the remaining cases that our large segment strategy couldn't handle. So we kind of covered in. I mean, the small segments is not down here where we'd like it to be, but it's definitely also better than the version using the segment scan. So basically we can stop here and say, yes, we're happy. We can kind of solve things. But we also have a trick up our sleeve, which is the last strategy. And that's simply using a single thread to process a whole segment sequentially on the GPU. And to do that, again, we have to do the transpose trick to be able to get memory coalescing. Ask me later if you want the details. What performance do we get? It's in green here. So initially we have just 1 segment, so we're only going to use 1 thread to process all 67 million elements. So it's going to take a long while. Once we get more segments, that means we're using more threads, so we get better and better performance. And you might be wondering, what's this one doing? And we are having an extra cost for doing the transpose in this case, so that's why it's kind of bumpy. For the last one, we don't need to do the transpose because it's just a single element. So we don't do the transpose. We need to write a bit more elements though, that's why it's also higher. So this is kind of the core of the work. Like we have these different strategies and we want to decide between them. So how do we do that? Well, we just devised a very, very simple way to pick between these 3 things. So we'll do this at runtime. If you have an input array with a number of segments, segment size, we say if the number of segments is so big that we think using the sequential segments is good, so multiplying this optimal number of groups by the group size, we'll use that one. We'll do the transpose to be able to get memory coalescing. Otherwise, if we can fit 2 segments within a group, that means using the large one will be horrible, so we'll use the small one. And for the remaining cases, we'll use the large strategy. So we'll calculate the chunking factor and the number of segments, or number of groups per segment as defined before. If it's commutative, we'll do the transpose to be able to do memory coalescing. And then we will apply the large strategy. If we used more than 1 group per segment, we'll have to recursively reduce the segments to end up with a single result per segment. Yeah, so we can look at what strategies we'll choose for the different ones, and we can see that marked by the black circles here. And I'm actually pretty happy about this. Like for these cases, it chooses the right one. So all is happy, all is dandy. Until we start looking at other examples. So this is a small example. It's only using 2 to the power 18, still doing a segmented sum. We can see for this case, the small one is actually better than the sequential segments. And that's going to trick our algorithm. It never saw that coming. So because in the end, we have so many segments that we can use a lot of threads, then we'll pick the sequential, even though it's not really the optimal choice. This is still the simple algorithm we use to choose a strategy, but I'm just saying it's not perfect. Right, so that's pretty much the core of it. If you have your own GPU library, now's the time to run away and start implementing this. Otherwise, I'll talk a bit about some benchmarks and the implication this has. So we're running some micro benchmarks. We're again comparing a bit against our old implementation and against a non-segmented reduction. We're also comparing against NVIDIA's COOP library using CUDA C++ code. And again, we're running on this NVIDIA K40. The COOP library supports irregular segment reduction, meaning that the segments don't need to have the same size. So that's a more general problem, and they can't really exploit the number of segments and segment size because they don't really, they know the number of segments, but they don't know like the size of them. So this is pretty much the same as before, except for this brown line. That's the COOP performance. And what they do is fairly simple. They use one group per segment. So initially, when there's just one group doing all the work, it's really, really slow. And then when there's more segments, it gets better. Until here. This is where it stops. Because at this point, it crashes. So CUDA has a limitation on how many groups can be launched at once, and that's 2 to the power 16. So when COOP goes to this point, it crashes. Now, let's just say that CUDA didn't have this limitation. What would then happen? Well, because still, you're just using a single group, at some point, their performance would do like this. Like it might be a bit later, like one step later, but there's a minimum group size that you can use, that you have to use to get good performance. So even if it didn't crash, it would still not be as good as ours in the later cases. Okay. Just gonna briefly mention this case as well. There are more in the paper if you want to look at more details. It's the maximum subarray sum. The problem is for each segment, find the continuous subarray with the largest sum. And this is interesting because it can be solved using non-commutative segmented reduction. And that means for both the large strategy and for the non-segmented, we need to do this transpose to ensure memory equalizing. And there's no COOP comparison because COOP requires that your reduction operator is commutative. So we won't see that. And what's the performance like? Same again, runtime, like compositions of a number of segments, segment size. And again, the large one is pretty close to or identical to the non-segmented. Again, we use the same strategy, no surprise. However, because we are doing transpose for these ones, and we're also doing that for the sequential segments, that one has high throughput, so it gets better performance, even than our non-segmented. So that's pretty good. It kind of opens up the idea that we might need to look into some more future work on improving the base one. And indeed, that is a part of our future work. So just quickly, I want to show the impact on 2 real-world benchmarks. It's kind of the whole point. So far, we've seen, yeah, you guys developed this thing, is it useful? Does anybody care? And this will show you, yes, somebody cares. So these are from Wriedt. We're comparing against the OpenCL implementation. Again, NVIDIA K40 to run our results. There's some configurations if you want to run them yourself. What we see in blue is the Wriedt OpenCL implementation. In red is the old implementation using segmented scans. And in green, we have our implementation for segment reductions. And we can see an improvement all over. So that's very good. We have the benchmark, which is neural networks. And we have k-means clustering with 2 test cases. Speedups are listed down here. That's pretty good, I think. And if you look at the proportion of time spent computing segment reductions from the 2 FUTAC versions, we can see an improvement from 20% or more down to 1 or 2%. So at least I'm really happy about this. This really means that the work we did had a good impact. It's actually useful for real programs, and that it's probably not worth it's not worth investing your time into trying to optimize this more before you have solved other problems. Should also be said that these ones all hit the large strategy case, so it's not really it's not really a good test of the ones we saw on the other side of things. Related work. So there's a good deal of related work on solving these irregular segment reductions, where the segments don't necessarily have the same size. There's also some work that support regular segment reductions, like Accelerate, but they have a very simple implementation, again just using 1 group per segment. There are more details in the paper if you want to know. So, to conclude, we've seen that we use 3 different strategies for regular segmented reductions on GPUs. And we have seen a similar procedure to dynamically choose between the strategies. We demonstrate a prototype in the FUTAC compiler. That's available online, all this code is merged in the master. Go ahead and play with it if you want. We've seen that the performance of the generated code is better than the one using the segment scan. And we've seen that they actually occur in real programs, or at least in real benchmarks, and that we actually improve performance for these. Future work, as I said, this work kind of opened our eyes to the fact that our non-segmented reductions is not perfect, and maybe by not chunking, meaning not making each thread read multiple elements, we don't have to do the transpose, and we might actually be able to do that faster. We haven't done that yet, so future work. And lastly, oh yeah, I forgot that. So we want to refine the decision process for which strategy to choose. I'll just try it as fast as possible. Skip back. Let's see, this one. I actually want to illustrate something. I forgot that. So our simple strategy isn't really aware of the whole commutative and non-commutative thing. So in these cases, it should definitely have chosen the sequential strategy here, right? And basically, there's a lot of variables going into this, like what machine are you running on? Are you running commutative, non-commutative? What's your reduction operator like? Like how many registers will it take on a GPU? How long does it take to compute? All those kind of things will impact which strategy is the right one to use. And obviously, the amount of data you're trying to process. So really what we want to do is make an answer tuning project for this. Yes, that's it.
Questions?
Yes, I really like your recommendations. One thing I'm a bit confused about, your transposition is basically just a reordering of
Yes.
the impediments. Why does that take such an overhead? Because surely you could do that with some sort of like pull array style thing where you just change where your functions are indexing into your data instead of actively reading it and then writing it, which is what I assume you're doing, right?
Yes, well, no, you can't really do that. To get memory coalescing, you really need to reorder the data. And you could...
No, but I do a similar thing that's not my work, where we need to get memory coalescing, but to do this we have basically a reordering that lets us get coalescing in this case without the overhead that you seem to have. I'm just a bit interested.
Okay, so I did some of the other projects that I actually documented the way they do this. They do a thing where they read things in, and then inside the group on the GPU, they kind of transpose it on the fly, and then they do the reduction afterwards. What we do is we do the transpose as a whole different step. So you do the transpose, read in memory, write out memory, and then read it into the reduction. So it might be possible to do that. If you have good ideas for doing it in a better way, please, let's talk about it later. I think we need to write something on paper to be able to discuss this properly.
Other questions?
So it was kind of interesting that the CUDA library dies right before the huge spike in overhead for that same strategy with the blue line.
Yeah.
I think the developers were aware that the performance is going to be very bad, and they didn't decide to try another strategy like you're doing. So they just let it crash, or I don't know. Is the crash assertion or?
So the crash is really you're trying to launch too many groups.
Oh.
You're not allowed.
Oh, okay.
So my guess is that nobody at NVIDIA ever tried to do this. I really don't know. Got a question?
Have you thought at all about irregular nested arrays?
Yeah, so I think that's a fair question. No, we have not. So all the food tag is really based on the assumption that we have regular arrays. And that's really what enables us to do these kind of things. There's some excellent work or excellent documentation for modern GPU, which is more of an educational project from NVIDIA, where they describe a quite nice strategy for doing irregular segment reductions. So if I had to do it, I would definitely use their strategy.
Questions? Thank you.